let's move on to the next talk by Dr. Prabodh Shukla from Northeastern Hills University, and he will be talking to us about comparing equilibrium states from partition function and dynamics.
So first things first, I thank the organizers of this meeting for organizing it, keeping the live contributions of Deepak and Mustansir in mind. In my reckoning, Deepak and Mustansir are the opening batsmen of modern StatMech team of India, and it's a matter of great satisfaction that they are still not out. I'm happy to have played the game in their times and at least done some fielding for the game. Now, coming to my short talk, its genesis lies in a recent puzzle when I was trying to verify an exact analytic result by simulations, and I failed to do so. So I'll mention it. I have 5 slides. I'll mention at the end of my slides. I mean, very sparsely written slides. All of them may look full to you. No equations there, and but since before sort of getting to that last slide and telling you what the puzzle was and why I couldn't sort of match the simulations with the exact result, I'd just like to discuss the broader perspective, in a couple of minutes. Can you now can I get back to my slides?
Yes, sorry. Yes, I'm sharing your slides. Could you check if you are able to see everyone?
Yeah, I can see the screen.
Yes, and is it
Yes.
you are seeing the slides or no?
Yes.
Yeah, okay.
So Prabodh, you can just tell me every time I need to switch, okay?
Yeah, so the first slide I have already sort of done by, I've said whatever I wanted to say. So let's go to the next slide. So next slide also, I mean, equilibrium is very important, but there are 2 ways to, calculate some equilibrium properties of a statistical system. One is by partition function and one is by doing dynamics. And we sort of tend to think that they should match. But as I said, I was trying to match the 2 and it didn't match. So, so let's skip over it, go to the next one. So 1D Ising model in a field. I mean, that's the only equation in my talk, and nobody needs an introduction to that. There are nearest neighbor interaction between Ising spins. There is an applied field H, and an important quantity that I will use later is HI. So HI is the local field that is spin fields at site I. And so the partition function can be calculated exactly. And therefore, the magnetization, equilibrium magnetization, can be, determined analytically. Unfortunately, the dynamics. First of all, dynamics has to be put in by hand. So the most popular dynamics is the Glauber single spin flip dynamics, and you'll be surprised. I was surprised that with an applied field on, even that dynamics cannot be solved analytically. So we have to, resort to simulations. And the important property of this dynamics is that it has detailed balance and ergodicity, and therefore, it thermalizes the system as time it sort of goes on in time. And it generates configurations with appropriate Boltzmann rates, and therefore independent of the initial state. So the moral that I take from here is that equilibrium state is something that is independent of the initial state. Can we go to the next slide so that I save a few minutes? Now the equilibrium is, concept of equilibrium is not as trivial as one would think. Given, just give me a minute. I have to, look at my slides on the phone, and the font is too small. So let me clean my glasses and, Okay, so what is equilibrium? I mean, so we say that you leave a system long enough, in contact with the temperature T, and the state which it reaches is the equilibrium state. But it's not a state which is sort of, which not, unchanging in time. There are many ways to describe equilibrium and its complexities. Feynman, in his book on StatPhys, page 1, paragraph 1, I think, says that equilibrium is when all the fast things have happened and all the slow things have not. But that also doesn't quite sort of, fit the bill for what I have in mind, because even in equilibrium state, I mean, there are equilibrium fluctuations at all time scales. And therefore, fast things are happening as well as slow things are happening. And, in this talk, I want to sort of say something about that. So can we go to the next slide, which I'll sort of, okay. So here is sort of, one-dimensional Ising model again in a magnetic field. And you see a yellow line somewhere in the middle. That is the equilibrium magnetization curve in the applied field H, which, as I say, is known analytically because the one-dimensional Ising model partition function in an applied field H can be evaluated exactly. The other hysteresis-looking curves, well, they are basically hysteresis, but not the usual hysteresis curves. So let me just, focus on the curve at the extreme right. I think it is probably, violet color or some such thing. So I start with magnetization -1. So this whole curve, from -1 to +1, it looks like a hysteresis curve in a changing magnetic field, but no. In this whole curve, I sort of start with all the time, I start with an initial state with all the spins down. And then by hand, I sort of increase the applied field in increments of delta H. And then I let the system evolve for T time steps, T Monte-Carlo time steps. T happens to be, if I can read my own writing, 100 time steps. And then, okay, so magnetization, increases, and when the applied field is very large, probably, about 0.5 on the scale of this figure, then after 100 time steps, all the spins which were initially all down, they turn up, and the magnetization becomes +1. So this thing, interesting thing is here, even when you start doing dynamics, that you discover a few things that you didn't sort of anticipate beforehand. If you do parallel dynamics, you get one curve. If you do sequential dynamics, you get another curve. So you can see the sequential dynamics is the one which is sort of next to the rightmost curve. And there, for the same given 10 time steps, the magnetization rises very quickly. So it's much faster. And then as I increase the time steps from 100 steps to 200 steps to 400 steps, the curve almost merges with the equilibrium magnetization curve that I knew analytically from the partition function. But the question is, the fact that these two curves merge with each other, does it mean that I have found, using dynamics, the same equilibrium state that the partition function gave me? And I think not. Okay. So next, when I did this, I also was curious. I happened to know also the result, well, not the analytic result, but at least a critical temperature on Bethe lattices. So next slide, please. So I play the same game on Bethe lattice with Z equal to 3 or more. Z equal to 2 is the same thing as one-dimensional Ising model. One new effect is seen here. The dynamic partition function cannot be evaluated exactly, as far as I know, even for this simple model in a given field H. But dynamics I can run, and And the new effect here seems to be a critical temperature. The dynamics, senses the presence of a critical temperature, and when you are, at larger than the critical temperature, then you get that, purple curve, and when you are much below the critical temperature, then you get that green-looking curve. And the problem here is that if you are at much lower temperature than critical temperature, the
2 more
curve
minutes,
never.
Professor Shukla.
Yeah, 2 minutes or 0 minutes.
2 more minutes.
Okay. So you as you run the dynamics again and again, it's the two curves never match. I mean, it just becomes very, very slow, and you never see what you would have hoped to see in equilibrium state. So so instead of sort of trying to find the equilibrium state from dynamics, the sort of game for me seemed to become how to sort of find more and more efficient dynamics. And I did 2 spin flip dynamics and 3 spin flip dynamics, and curves that I could not show you now. But the general idea is that as I do more and more spin flip dynamics, I reach what I expect to be an equilibrium curve for magnetization on Z equal to 3 lattice in an applied field. But in the absence of fluctuations, large fluctuations, difficulties of simulations, I would never know whether I have reached the same equilibrium state as I expect from the partition function. That's more or less was the idea that I wanted to convey. Thank you.
Thank you, Professor Shukla.